Presenting our CDR presentation. This is Group 19 with our Computerized Automatic Rapid Deck Sorter, or CARDS for short.
Hello, my name is Emily Gensch. I'm a computer engineering major. I am the project manager and the mechanical lead.
Hello, my name is Henry Apshire. I am also a computer engineer and I was the hardware lead for this project.
Hello, I am Nicholas Heikes. I am a computer engineering major and I am the software lead for this project.
Hello, my name is Benjamin Harris. I'm an electrical engineering major and I'm the electrical lead for this project.
Our project is an automated card sorting machine. It demonstrates the functionality needed for currency processing. While the machine will accept playing cards in any orientation, whether it's face up, face down, or rotated, it will automatically detect, orient, and sort them into organized stacks. Using sensors and mechanical components, it will identify card positioning, correct alignment issues in real time, and efficiently organize cards without human intervention. This proof of concept will validate the technology's ability to handle the variable conditions and orientations that banking machines currently struggle with, paving the way for currency processors that can accept bills in any configuration while maintaining speed and accuracy.
Now, let us talk about the motivation behind our project. Currently, banks face a challenge where bills must be manually oriented before processing. Tellers spend significant time aligning deposits, and ATMs require customers to pre-orient bills, leading to longer wait times and frustration. This inefficiency increases operational costs, reduces customer satisfaction during busy periods, and risks human error in sorting. Our market need to develop an automated sorting technology using playing cards as a proof of concept, eventually handling currency and bills in any orientation. So why playing cards? Well, first, they share similar properties with currency, paper-based construction, and a rectangular shape, making them a great stand-in. Their smaller size and better grip reduces mechanical issues during our development time. Plus, they're cost-effective, allowing extensive testing without the security protocols that real money requires. And with no regulatory complications during the prototype phase, they ensure safe development. Now, to define our objectives and goals. Our objectives are to develop a detection mechanism to identify card orientation, design jam prevention for the various card conditions, and to test the machine's efficiency under different scenarios. Our goals: first, the machine will automatically orient and align playing cards to a uniform state, regardless of their initial position. Second, it will stack cards neatly for easy handling. Finally, it will operate with minimal user intervention using an intuitive interface.
The engineering specifications we chose reflect our design goals as a team. First is power consumption. We're aiming to stay under 60 watts since that's the limit of our power supply. Ideally, we'd like to keep it below 45 watts. Next is throughput, which we are defining as how quickly cards are dispensed after the first card reaches the output. Our target is at least 2 cards per second. We're also focusing on sorting accuracy and error detection. We are aiming for at least 98% of cards sorted correctly and 90% of errors detected. For capacity and weight, we're aiming for a 50 card capacity in the input box and a total system weight under 5 kilograms. We are also intending for our design to have high card detection accuracy and fast color processing, with sensors correctly identifying a card in the entry box 98% of the time, and the color of the card being detected in less than 100 milliseconds. Finally, our target operating temperature is 0 to 55 degrees Celsius, and we want to keep the unit cost under $100.
This hardware block diagram shows the core components of a robotic system. Power flows from the delivery board through the main control board to coordinate 5 key motor groups: the entrance roller, flip and rotation motors, along with our sensor array, including rotation, dock, exit, and orientation detection, color sensors.
The first portion of our system is the entry box. The entry box allows for between 1 and 100 playing cards to be inserted into the system. However, only 1 card will be fed through the system at a time. This ensures that a steady and controlled intake occurs, preventing jams or misfeeds. The next portion of our design is the color scanning station. It serves a dual purpose for allowing us to see which orientation the card is facing, whether it is up or down, as well as using an infrared sensor to let us know that one card has in fact entered the station as a protection module to ensure that only one card is moving through the system at any given point. The third point of our system will be the flipper station. If the scanning station detected that a card is facing the wrong side up, the machine will have the flipping mechanism activate. This automated feature precisely rotates the card to its correct position before moving it further forward for further processing. The fourth part of our system is the rotation station. The rotation station's main function is to be able to sort and organize the cards, depending on their colors, into the correct output box, which is the final portion of our system. The final portion of our design will be the exit box. Once the cards have been fully processed by the rotation station, they are neatly delivered to one of the output trays in a uniform and well-organized stack. This feature allows for easy retrieval and handling, ensuring that the processed cards remain neatly organized and ready for use.
Moving on to hardware components. So when looking at motors, there are three major factors we're looking for: size, power, and energy consumption. We have a lot of moving parts in our project, and we need to make sure it kept small footprint to stay within the desk space that we were aiming for. And so we needed something that was small enough but had strong enough power. The chosen one we went for was the G12N20. Not only is only a couple millimeters in length, it is only 10 grams, but can output a solid torque, as well as the fact that it does not generate a lot of heat and can operate on low as 20 amps. For the servo motor, size and power were less of a consideration. We were mainly focused on reliability. Those are very light, as well as being easily catch air. So we needed something that was able to really pinpoint the exact dimensions, lest the bills get put off track and will fly away. We ended up deciding on the Stepper Online 17H SO8 because not only was it reliable, it was also a very small footprint, also coming in at only a couple centimeters. Sort of thing, as well as having a decent amount of torque, as well as good energy uses.
The motor driver we've selected for our G12 N20 motors is the DRV8912, a multi-channel half-bridge driver with advanced diagnostic capabilities. We chose this driver for several reasons. First, it supports up to 6 full H bridges per chip, which is ideal for our design since we're using multiple motors. Second, the DRV8912 uses SPI communication, which allows us to connect and control multiple drivers over a single SPI bus. This is especially useful in our case since we need more than 6 motor channels, meaning more than one chip. SPI also enables high-speed switching between drivers, ensuring responsive control during operation. Another major benefit is the built-in diagnostic features, such as the fault pin, which allows us to monitor faults in real time and protect the system from overcurrent conditions through firmware. Finally, the DRV8912 supports PWM control, giving us precise control over motor speed, which is critical for ensuring consistent and swift throughput and sorting accuracy. The motor driver we selected for our stepper motor is the DRV8825, a dedicated stepper motor controller IC. It includes 2 full H bridges, which is exactly what's needed to drive a single bipolar stepper motor. This is perfect for our application since we're only using one stepper motor. The DRV8825 is controlled using a step direction interface, where each pulse on the step pin advances the stepper motor, and the direct pin sets the rotation direction. The DRV8825 also features a fault pin for real-time fault monitoring, and built-in overcurrent protection that disables the output if the current exceeds 3 amps, helping prevent damage. Lastly, the DRV8825 includes an internal 3.3 volt regulator to power its own logic circuits, so it doesn't require an external 3.3 volt supply for operation.
Moving on to the sensors, we wanted some way to track bills/costs as they move through our process. We have a lot of motors, moving parts, and gaps, and we want to be able to determine if a bill got stuck or jammed. The way we decided to do this was have sensors in between each station, so we have a running tally of which bills end up where on the time as they went throughout. We decided on something super low tech, so it didn't have as much variability, and so it was very reliable as well as cheap to produce. And so we decided on the H2010 and LM393 IR sensor. It's a very simple IR beam, phototransistor, and voltage regulator circuit that outputs low whenever a beam is broken, These are located at the intervals between each station, and as cars move from one station to another, it trips the beam, therefore alerting the microcontroller that the car has made it to the next station. As part of our project, the color sensor was the crux of the project. If this is the heart of the system that really determines how we are able to detect which orientation the build is and now which orientation cards are. For this, we really spent a lot of time looking over the different parameters as well as different axes. What we eventually decided on was the TCS34725 Adafruit color sensor. The reason why we chose this sensor over any of the other ones was not only a small footprint, but specifically it allowed for 8 different channels of different wavelengths of light and allows you to access them all simultaneously. This allows us to compare multiple different wavelengths of light at the same point in time, which is instrumental when you're dealing with playing cards or with builds which have multiple different colors going past at the same point in time. This allows us to give each orientation of a build/playing card its own unique color signature as it moves through, allowing us to determine the orientation without much processing power. For our body material, we wanted to go with something that was cheap, reliable, heat resistant, but also was able to be made in such custom shapes, which allows us to get the best use out of our motors as well as all other components, giving us the freedom and capability to position them in the most optimal location. So we decided to go with a 3D printed enclosure, specifically using ABS plastic. We chose ABS plastic over PLA or PETG or other types of plastic due to its reliability as well as wet resistance, but most importantly, its heat resistance and rigidity. We have a lot of motors in our project, which introduce a lot of vibrations into the system. ABS is really good at resisting those vibrations, as also having a much higher heat resistance than something like PLA, which tends to melt in the sun. And so, if our machine is meant to be on the bank teller's desk or player's desk, they might be left in the window, as well as being able to have lots of motors in it, could generate enough heat to melt the out microplastics.
For our project, we initially selected the Arduino Mega due to its extensive I/O capabilities in familiar development environment. However, after further testing and research, we realized that electrostatic discharge was going to be an issue later in development. As such, we pivoted to the ESP32. It would not have been our first choice, however, it is cheap, reliable, and it would not be difficult to add on a couple of multiplexers to get the number of pins that our project needs. It is also heavily used in projects such as this one, so it was not a hard pivot.
To move the bills of balance, we decided to go with Rike AF03 1081 rollers. These were taken out of printer rollers for the rear family. We decided to go with printer rollers because not only are they cheap, readily available, and affordable, but most importantly because they are tried and true and they have specifically designed to pull grip on very lightweight, flexible objects such as paper. This allows us to leverage the use of R&D development these printer companies have done for our own hobbyist project. This is the overall software block diagram. It's kind of long, so we're going to break it down chunk by chunk. One of the issues we first encountered when designing our project was that more than one build will oftentimes be taken by the roller. This is inconsistent and can depend on the type of shape of the build, shape of the cards, wear and tear, lightness, type of crosstalk used. And so in order to help get more consistency in our process, we developed a detection algorithm. It's very simple. We have 2 color sensors which are used to help determine the orientation of the build, positions above and below the build. Using the LED on the bottom one, we can determine the brightness read by the top sensor. One card is enough to block most of the brightness, while 2 cards completely block the brightness. And so, if the top sensor cannot detect brightness from the bottom sensor, we know for a fact that more than one bill is in the system, or something unexpected has entered the box. And so in that case, we run the motors in reverse to remove whatever blockage before we begin running it back and forth. As we mentioned before, another one of our common errors is having the card/build get stuck in between the substations or systems. And in order to help detect this and prevent any catastrophic errors, which is very important when dealing with high amounts of currency, is we have a jam detection algorithm. What we do is that we have IR sensors at each of the substations. As the card/build passes through each station, it trips the tripwire sensor. When this is done, it resets a timer that's on the ESP. What this allows us to do is, at any point, if the card gets stuck, it never reaches the next tripwire sensor, and so the timer will expire. When the timer expires, we know, okay, it hit this station but never made it to this station. So we know exactly which substation has the error and can report back to the user to inform them, hey, we have an issue here, we need to stop here. Also prevents any further damage happening to the bill and/or flash cards. One of the more complicated stations is the flipper station, which flips the cards from face up to face down, and vice versa. We start by when the card enters the system, and then we check to see if the flag for face up or face down has been set by the color sensing station. If it's face up, then we need to flip it. If it's face down, we can just turn on the motors and send it directly to the next station before going back to check the next card. If it's face up, then what we do is we turn off the second motor, keep the first motor on, which is the stop block, turn off the first motor, turn on the flipper motor, flip the card, and then turn on the second motor to pull it into the next station. And then it goes back and checks for the second one. Lastly, for our software flowchart is the rotator software flowchart. What the rotator does is that once it gets the card from the color sensor, from the flipper station, it knows whether or not it needs to go into, at most, 3 piles. And so we have the first pile, second pile, and the third pile. Depending on which parameters are set or where we're checking for, it stepper orientates itself to one of the 3 piles and sends them in there. For example, if we were going through like red suits, black suits, and cards that do not belong in the deck, what we would do is we'll go ahead and then send the red suits to the first pile, black suits to the second pile, and then any card that fails either red or black test goes to the third pile, the reject pile. This can be configured in software, and we are hoping as a stretch goal to add different configurations for different types of parameters that a user might want to look at.
For our development environment, we chose the Arduino IDE due to our team's existing experience with the platform. We programmed the ESP32 using C in the Arduino Programming Language Framework. To streamline our development process, we utilized several libraries: the Arduino ESP32 board package for hardware support, the Adafruit library for sensor integration, and the DRV 8912-Q1 motor library for precise motor control.
Our PCB mainboard is dedicated to handling the system's core components and power distribution. It is powered by a 12-volt barrel jack, which receives power from a 60-watt AC to DC converter. The board hosts the USB programming interface, the ESP32 microcontroller, the USB to UART bridge, an I2C multiplexer for the color sensors, and the connectors for motor and sensor outputs and inputs. To reduce complexity and manage space, we place the remaining components on the breakout boards, with their footprints clearly marked on the main board. This ensures that no components are placed underneath them, maintaining clearance and minimizing EMI concerns. The breakout boards interface with the main board via pin headers. The overall dimensions of the main board are 150 by 150 millimeters, and it includes a ground port on both the top and bottom layers for improved noise, performance, and signal integrity. The DRV8912 breakout board is dedicated to housing the DRV8912 IC and its supporting components. It interfaces with the main board through 2 sets of pin headers in 2 locations, since our design uses 2 DRV8912 chips to control a total of 10 G12N20 motors. These pin headers provide connections for the 12-volt power rail, the 3.3-volt logic rail, the ground rail to maintain a common ground, the SPI bus, and all motor output lines. Additionally, the fault pin from both DRV8912s are routed through the headers to dedicated ESP32 GPIOs for real-time fault monitoring. Given the DRV8912's low active power consumption, we chose not to dynamically toggle its sleep mode. Instead, we keep the device continuously enabled and ready for use by pulling the sleep pin high with a pull-up resistor. Lastly, decoupling capacitors are placed close to the power and logic input pins to reduce noise and ensure stable operation. Similarly, the DRV8825 breakout board is dedicated to housing the DRV8825 IC and its supporting components. It interfaces with the main board through a single set of 5-pin headers, since only one DRV8825 is needed to control our single stepper motor. The headers provide connections to the 12-volt power rail, ground, motor output lines, and dedicated ESP32 GPIO pins for the step, direction, and fault pins. A connection to the 3.3-volt rail from the main board is not required, as the DRV8825 includes its own internal 3.3-volt regulator to power its logic circuits. To set the appropriate current limit for our stepper motor, we use the DRV8825 datasheet and a voltage divider on the VREF pin to configure the internal current regulation. The sleep pin is pulled high using a pull-up resistor to keep the device continuously active. Lastly, the breakout board includes decoupling capacitors placed near the 12-volt input and regulator output pins to reduce electrical noise and ensure stable operation. The regulator breakout board houses the LM2576 12-volt to 3.3-volt buck converter and its supporting components. It connects to the main board through a single set of 3-pin headers, which provides access to the 12-volt rail, 3.3-volt rail, and ground. The LM2576 buck converter is used to supply 3.3-volt power to the ESP32, the logic rails of both DRV8912 motor drivers, the color and IR sensors, and the I2C multiplexer. The board was designed in accordance with the LM2576 datasheet, incorporating a Schottky diode for efficient switching and a properly sized inductor capable of handling the regulator's full output current.
Now, as for the work distribution, our project lead is Emily Gensch as project manager. Benjamin Harris leads electrical work, including PCB and power systems design, while Nicholas Hikes handles primary software development for sensors and system integration. Emily also manages mechanical design and 3D modeling, with Henry Amshire supporting both software and hardware implementation. Here is a breakdown of our project budget so far, which totals $711.17. Our largest expenses was the motor driver development board, the PCB fabrication, and all the different PCB components. Overall, not the most expensive senior design project, but there is another month before this thing is due, and problems and revisions will arise, and they will need to be taken care of. However, we are staying mostly on budget so far and will continue to stay on budget in the future.
Prototyping has foreseen us many challenges. However, we have overcome each and every one of them to this point, and we will continue to do so all the way to the end of our design. The next clip we'll be showing is going to be our entry box, demonstrating that we can in fact put one card into the system at a time, regardless of how many cards are in the entry box. Please enjoy. Now that you've seen some of our success with our project, let's talk about the issues that have constantly plagued us throughout our project's progress. Card detection complexity. Initially, we explored using computer vision with a camera module for card orientation detection. However, our research revealed that even lightweight machines' learning algorithms require computational resources far beyond what our target microcontrollers could provide. That is especially true with the amount of RAM that would be required and the board that would need to accompany it. The mechanical precision. Ensuring consistent card movement through the system required precise tolerances and alignment of components. This led us to have to continuously print and reprint our design. Integration complexity. Coordinating the various sensors, motors, and mechanisms presented a significant challenge. Having so many components in our system, it became quite a challenge to be able to make sure that each motor is independently controlled at all times. Budget constraints. Working with our self-imposed budget of $450 required careful component selection and cost optimization. We have since gone over this budget significantly, almost doubling our initial assessment. Now let's talk about the solutions to some of our issues. For the card detection complexity, rather than introducing the additional complexity of external server processing, we pivoted to a more efficient approach using specific color patterns detected by the AS7341 sensor, which proved to be both reliable and computationally feasible. For the mechanical precision, through iterative prototyping and testing of critical elements like the custom gear shaft connectors and rollers, we achieved reliable bill handling without jams or misfeeds. For the integration complexity, our solution involved developing a state-based software architecture that managed transitions between different operational stages while maintaining proper timing and synchronization. Budget constraints. By leveraging 3D printing for custom parts and prioritizing essential components for quality while finding cost-effective alternatives for secondary elements. This is especially true for our 3D printing, as we are privileged enough to have the university provide free 3D printing services for senior design. On behalf of Group 19, we'd like to say thank you so much for watching our video and providing us constructive criticism so that we can better and more efficiently improve our project.